Hello, I'm Seema and welcome to part 41 of the chapter Hydrocarbons. We have been studying about aromatic hydrocarbons, and in this topic I told you about the nomenclature and isomerism of hydrocarbons. Then we started discussing the structure of benzene in the past few videos. We have talked about the structure of benzene. I told you how Kekulé devised the structure and he gave the Kekulé structures, but the Kekulé structures of benzene could not explain the extraordinary stability of benzene. And therefore, the concept of resonance was introduced, which I explained in the previous video, that is in part 40. So after having studied about resonance and why benzene is so stable, we now come to the next topic, that is aromaticity. Benzene is not the only aromatic hydrocarbon. We've studied about the other ones also when we did the nomenclature. Which is a compound that we would call an aromatic hydrocarbon? What is it that makes the compound aromatic? Or what is aromaticity? Aromaticity is a characteristic of a compound, like in the case of benzene we saw that due to resonance, the behavior of the molecule, although it is unsaturated, it shows a different kind of a stability like a saturated hydrocarbon. It shows substitution reactions and it is a more symmetrical structure due to resonance. So now we will try to understand which are the compounds which would be called aromatic hydrocarbons. What is it that made benzene aromatic? Two properties we've already studied. There are three characteristics that make a compound aromatic. And we have studied the first two in a way while I was explaining benzene to you. The first, if you remember, I told you in the previous video that the structure of benzene, when we were discussing the structure of benzene, that benzene is a planar molecule. All the carbons are sp2 hybridized, and being sp2 hybridized, they form a planar triangular. Around every carbon you have a triangular planar structure. So all aromatic hydrocarbons are planar molecules. And the only thing that is there is the unhybridized p orbitals, which are perpendicular to that plane. And those are supposed to be forming the multiple bonds. And if you take a look at benzene, you see it has alternating double bonds, right? And whenever you have these alternating double bonds, only then it is possible for the electrons to shift and form and to get delocalized. So, first condition for a compound to be aromatic is that the molecule should be planar. Second is that there should be complete delocalization of electrons. And complete delocalization is only possible if there is alternating pi electrons. Pi electrons or multiple bonds, double bonds should be alternating. Only then the shifting of electrons is possible. Imagine if there's a double bond here and there was a double bond here also. Then the pi electrons would not have been possible for the pi electrons to shift to a space which is already occupied by electrons, because there would be too much of repulsion between electrons. So this is another condition, that there should be complete delocalization of pi electrons, which you should understand is possible only if there are alternating pi electrons. Now pi electrons will not be just the multiple bonds, that is the electrons of a pi bond. The electrons of lone pair, the lone pair electrons, they also can act as a site, that is, they also can participate in the resonance. Similarly, a positive charge, that is a lack of electrons, also can act as that point where electrons can move and therefore lead to resonance, therefore cause the delocalization. So if there is delocalization, complete delocalization, only then resonance will take place. So the second condition is that there should be complete delocalization of pi electrons in the ring. In the ring, every word here is important. In the ring means all of these compounds, if you look at them, the aromatic hydrocarbons, they are cyclic in nature. They have to be in the form of a ring. If they are not in the form of a ring, complete delocalization is not possible. If you imagine that this hexatriene was a straight chain compound, then how could the electrons be free to move around anywhere? If it's a straight chain, it ends here, it ends here. The electrons move in this direction and that direction, but they do not just move in circles. So the molecule has to be in the form of a ring. It has to be a circular molecule. Circular means it should be in the form of a ring. The ring may be in any shape. The end and the beginning should be joined together. And then there should be complete delocalization. And the third condition, these two conditions indirectly you have understood when you studied the structure of benzene. You saw that the structure is planar. You saw that it is a circular molecule. It's in the form of a ring. You saw that the electrons, the pi electrons, are delocalized. You also saw that the delocalization was because they were alternating double bonds. Then the third rule, which is very important for if you look at compounds and you have to see whether the compound is aromatic or not, what will you see? The first step you will see, is it a ring? Is it cyclic? It should be a cyclic hydrocarbon. Second, it should be a planar hydrocarbon. All the carbons should be sp2 hybridized. It should be a planar molecule. Then even if it is not sp2 hybridized, it should be in lying, that particular carbon also should be lying in the same plane. There should be a complete delocalization of pi electrons, and third, it should follow Huckel's rule. What is Huckel's rule? Huckel's rule is the number of pi electrons. The number of pi electrons should always fall in the formula 4n plus 2. The compound should have 4n plus 2 number of pi electrons. What is n? N is an integer. N is a number. So 4n plus 2 number of pi electrons should be there. Now let us take benzene first. Benzene is planar. Yes. There is a complete delocalization. Does it have alternating double bonds? Is there a possibility for electrons to be delocalized? Yes, if there are alternating pi electrons, there is a possibility of delocalization. Does it follow Huckel's rule? Does it have 4n plus 2 electrons, pi electrons? Now, how many pi electrons are there? The pi electrons should follow Huckel's rule. So, if you take, it has 3 double bonds, therefore it means it has 6 pi electrons. Every multiple bond that is a pi bond has 2 electrons. So there are 3 pi bonds, therefore there are 6 electrons. 6 electrons means the value 4 into 1 is 4 plus 2 is equal to 6, which means the value of n for benzene would be 1. Right? There are 6 pi electrons, it follows Huckel's rule. Look at this now. This is cyclopentadienyl anion. It's an anion. At this point, there's a negative charge and there's a lone pair of electrons here. Lone pair of electrons also act as if they are in conjugation. What is conjugation? If they are present as alternating. If they are also present in a situation where they alternate with the double bonds. If they are in the conjugation, they can also participate in resonance. So this is a pentagonal molecule. If you see, it is planar, therefore, and does it follow Huckel's rule? How many pi bonds does it have? It has 2 pi bonds, but it has a lone pair of electrons also, which are also treated as pi electrons, because they are free, they are not bound, they can also be delocalized. They can also participate in resonance. Therefore, this also has 6 electrons. 6 electrons means the value of n will be 1. 4 into 1 is 4 plus 2, 6 electrons. So it is an aromatic hydrocarbon, or it shows that this molecule has aromaticity. Right? What is aromaticity? The same thing. Whether you call it has the property of aromaticity, or is it a hydrocarbon, an aromatic hydrocarbon, you can classify it as an aromatic hydrocarbon. Look at this again. This is a cycloheptatrienyl cation. Now, if you really see, it is hepta. It has got 7 carbons and it has got 3 multiple bonds. Unlike a an anion where a lone pair of electrons is present, where the positive charge is there is no electron in a positive charge. Positive charge means lack of electrons, that it is deficient in electrons. So the electrons are less. Whenever you have less electrons or positive charge, that can also help in resonance. Why? Because being positively charged, it will have a tendency to attract the pi electrons. And since it is also alternating, there is a single bond here and then the positive charge is here. There's a multiple bond, that is double bond here, single bond here, and a positive charge. Then single bond here, a double bond, single bond, double bond, single bond, double bond. So this also kind of comes in a point. This positive charge starts acting as a double bond. Although it has no electrons, but it helps in pulling those electrons and shifting them further. Because due to resonance, the electrons are not going to stay at the positive charge, they are going to move on. So it participates in resonance, and therefore this is also an aromatic hydrocarbon, and it follows Huckel's rule. What is Huckel's rule? It has 6 pi electrons. Here there are no electrons. It has 6 pi electrons, 1, 2, 3 double bonds, therefore 6 pi electrons, so 4 into 1 plus 2. This also follows Huckel's rule. Now comes the second category, that is naphthalene. Naphthalene is 2 benzene rings fused together. This molecule has this formula, if you really look here. 2 benzene rings fused together and there are 5 double bonds. And look, they are all, is it a planar molecule? Of course it is planar. Can it have complete delocalization of pi electrons? Does it have alternating double bonds? Look, double bond, single bond, double bond, single bond. Double bond, single bond, double bond, single bond, double bond, single bond. So yes, the electrons can be completely delocalized. So yes, it can be completely delocalized. Therefore, the second condition is also fulfilled because it has alternating double bonds. The third, does it follow Huckel's rule? How many pi electrons does it have? It has 5 pi bonds, therefore it has 10 pi electrons. So if it has 10 pi electrons, 4n plus 2 is equal to 10. If you solve it mathematically, 4n plus 2 is equal to 10. So what is the value of n? N will be, 4n would be equal to 10 minus 2, which is equal to 8, and n would be 8 upon 4, which is equal to 2, which is a whole number. So, which shows that yes, since it is a whole number, it has a proper value of n. The 10 electrons also follow, the 10 pi electrons also follow Huckel's rule. Therefore, naphthalene is an aromatic hydrocarbon. Next is anthracene. Anthracene is 3 fused benzene rings, and so is phenanthrene. Phenanthrene is also 3 fused benzene rings, but not linearly, it is slightly in the other direction. So look at the number of multiple bonds here. The number of multiple bonds again is seen to be the same, 1, 2, 3, 4, 5, 6, 7. There are 7 double bonds. Therefore, 7 twos are 14. So does it have a whole number again? If 7 twos are 14, do this again. 4n, let me do it here. 4n plus 2 is equal to 14. Does n come out to be a whole number? So 14 minus 2, n will be equal to 14 minus 2 upon 4. 14 minus 2 is 12 upon 4 is equal to 3. So it has a whole number, value of n. Therefore, this also follows Huckel's rule. And therefore, this compound anthracene is also an aromatic hydrocarbon. Similarly, phenanthrene is basically the same molecule, same number of multiple bonds also, 3 benzene rings fused together, only the shape is different. So if you see, count the number of multiple bonds, 1, 2, 3, 4, 5, 6, 7. It has 7 multiple bonds, which means double bonds or 7 pi bonds, or 7 pi bonds means 14 pi electrons. 14 pi electrons is what system? It is n is equal to 3, therefore it follows Huckel's rule. So these are the conditions for a compound to be aromatic. Now moving on to the next subtopic here, the preparation of benzene. Coming back to benzene again. We'll talk about the preparation and the properties of benzene. There are three methods of preparation of benzene mentioned in your textbook. The first is cyclic polymerization of ethyne, which we have already done. In which topic? The cyclic polymerization, where we were talking of the chemical properties of of alkynes. In chemical properties of alkynes, we have done this reaction, the cyclic polymerization of ethyne. These are three molecules of ethyne. When you pass three molecules of ethyne, or actually when you pass ethyne through a red hot iron tube at 873 Kelvin temperature, what happens? Three molecules of ethyne, they arrange themselves in such a way that one bond on each ethyne breaks. When one bond on each ethyne breaks, each carbon gets back its electron. This carbon gets its electron, this carbon gets its electron, here this carbon gets its electron, this carbon gets its electron. So they form these electrons, they form single bonds. And when they form single bonds, what is formed? Benzene. So instead of those, wherever you had the triple bonds, one bond breaks and it forms a single bond here, one bond breaks here, it forms a single bond here, one bond breaks, it forms a single bond here, results in the formation of benzene. This is cyclization or cyclic polymerization. Three monomers join together to form a trimer. So it is cyclic polymerization of ethyne, takes place in the presence of a red hot iron tube at 873 Kelvin temperature. You will get benzene. What is the second method of preparation of benzene? You can get benzene by the decarboxylation of aromatic acids. What is the formula of a carboxylic acid? It is COOH, right? The functional group. It is COOH. So decarboxylation of aromatic acids, the sodium salts of aromatic acid. If you have COOH is the functional group for an acid, then the sodium salt of the organic acid would be COONA, right? So sodium salts of aromatic acids, so we take benzoic acid is an aromatic acid, decarboxylation of aromatic acid. Sodium salt of benzoic acid on heating with soda lime. What is soda lime? What is caustic soda? Sodium hydroxide is caustic soda. What is lime? Calcium oxide. So when you have the sodium salt of an aromatic hydrocarbon, so benzoic, sodium salt of benzoic acid or sodium benzoate, the sodium salt of benzoic acid plus sodium hydroxide, that is caustic soda, and calcium oxide is lime. When you heat these together, it leads to the decarboxylation. Decarboxylation means carbon and oxygens will be removed. Actually, the sodium is also removed. But when we are talking of decarboxylation of aromatic acids, we are not talking of sodium, we are assuming this to be hydrogen. So first we take the aromatic acid, make the sodium salt of it, then remove the carbon dioxide and the hydrogen comes back and results in the formation of benzene. So Na2CO3 is removed, the hydrogen from here would then get attached to form the benzene ring. So you get sodium carbonate. The third method of preparation is reduction of phenol. Phenol is a benzene ring to which OH is attached. So when you reduce it, what is reduction? What is oxidation? Oxidation is addition of oxygen. Reduction would be removal of oxygen. So if oxygen is removed from phenol, you will get benzene. So reduction of phenol is reduced by passing its vapors over heated zinc dust. So in the presence of zinc dust, you heat up the phenol, the vapors of phenol are passed over it, over zinc dust, because zinc is a metal and it has to be in the form of a dust to increase the surface area so that this reaction can take place, and it leads to the removal of the oxygen. It results in the formation of zinc oxide and the hydrogen gets attached here to form benzene ring. So these were the methods of preparation of benzene. In the next video, we are going to start the next topic, that is properties, the properties of benzene. And well, I'll do that in the next video. With this, I'll wind up today's video. If you want to watch the other videos of this chapter, please click the link that appears on top of your the video. And if you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos on chemistry. Thank you for watching, and bye-bye for now.